The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, today is all about the predecessor problem, which is a problem we've certainly talked about implicitly. Say binary search trees, you want to be able to insert and delete into a set and compute the predecessor and successor of any given key. So maybe define that formally. And this is our not really our first, but it is an example of an integer data structure. And for whatever reason, I don't brand hashing as an integer data structure just because it's its own beast. But in particular today, I need to be a little more formal about the models of computation we're allowing, or I want to be. In particular because in the predecessor problem, which is insert, delete, predecessor, successor, there are actually lower bounds that say you cannot do better than such and such. With hashing, there aren't really any lower bounds because you can do everything in constant time with high probability. So I mean, there are maybe some lower bounds on deterministic hashing. That's harder. But if you allow randomization, there's no real lower bounds. Whereas predecessor, there is. And in general, predecessor problem, the key thing I want to highlight is that we're maintaining here a set of S. The set is called S of n elements, which live in some universe, U, just like last time. When you insert, you can insert an arbitrary element of the universe. That probably shouldn't be an S, or it'll get thrown away. But the key thing is that predecessor and successor operate not just on the elements in S, but you can give it any key. It doesn't have to be in there. And it will find the previous key that is in S or the next key that is in S. So predecessor is the largest key that is less than or equal to X that's in your set. And successor is the smallest that is larger. Of course, if there is one. Okay, so those are the kinds of operations we want to do. Now we know how to do all of this in log n time, no problem with binary search trees in the comparison model, but I want to introduce two more, say, realistic models of computers that ignore the memory hierarchy, but think about regular RAM machines, random access machines, and what they can really do. And it's a model we're going to be working in for the next, I think, 5 lectures. So important to set the stage right. So these are models for integer data structures. In general, we have a unifying principle, which is or unifying concept, which is a word of information, a word of data, a word of memory. It's used all over the place. A word of input. A word is the machine theoretic sense, not like the linguistic sense. It's going to be a W-bit integer. And so this defines a universe, which is, I'm going to assume they're all unsigned integers. So this is 2 to the W minus 1. Those are all the unsigned integers you can represent with W bits. We'll also call this number 2 to the W little u. That is the size of the universe, which is capital U. So this matches notation from last time, but I'm really highlighting how many bits we have, which is W. Now, here's where things get interesting. I'm going to get to a model called a word RAM, which is what you might expect, more or less. But before I get there, I want to define something called a transdichotomous RAM. Tough word to spell. Just means bridging a dichotomy, bridging two worlds, if you will. RAM is random access machine. I've certainly mentioned the word RAM before, but now we're going to get a little more precise about it. So in general, in a RAM, the memory is an array, and you can do random access into the array. But now we're going to say the cells of the memory, each slot in that array, is a word. Everything's going to be a word. Every input, if you want, all these x's are going to be words. Everything will be a word, and in particular, the things in your memory are words. Let's say you have S of them. That's your spacebound. In general, a transdichotomous RAM, you can do any operation that reads and writes a constant number of words in memory. And in particular, you can do random access into that memory. But in particular, we use words to serve as pointers. Here's my memory of words. Each of them is W bits. There's S of them from, I guess, 0 to S minus 1. And if you have like the number 3 here, that is can be used as a pointer to the third slot of memory. 1, 2, 3. You can use numbers as indexes into memory. So that's what I mean by word serve as pointers. So in particular, you can implement a pointer machine, which no surprise. But for this to work, we need a lower bound on W. This implies W has to be at least log of the space bound. Otherwise, you just can't index your whole memory. Right? If you've got S minus 1 things, this 2 to the W minus 1 better be at least S minus 1. So we get this lower bound. So in particular, presumably S is at least your problem size, N. If you're trying to maintain N items, you've got to store them. So W is at least log N. Now this relation is essentially a statement bridging two worlds. Namely, you have on the one hand your model of computation, which has a particular word size. And in reality, we think of that as being 32 or 64 or maybe 128. Some fancy operations on Intel machines, you can do 128-bit or so. And then there's your problem size, which we think of as an input. Now, this is relating the two. It's a little weird. I guess you could say it's just a limitation for a given CPU. There's only certain problems you can solve. But theoretically, it makes a lot of sense to relate these two, because if you're in a RAM and you've got to be able to index your data, you need at least that many bits just to be able to talk about all those things. And so the claim is basically your machines will grow to accommodate memory size. As memory size grows, you'll need more bits. Now, in reality, I mean, there's only about 2 to the 256 what do you call them, particles in the known universe. So word size probably won't get that much bigger. Beyond 256 should be okay. But theoretically, this is a nice way to formalize this claim that word sizes don't need to get too big unless memories get gigantic. So it may seem weird at first, but it's very natural. And all real-world machines have big enough words to accommodate that. Word size could be bigger, and that will give you essentially more parallelism. But should be at least that big. All right, enough proselytizing. Then that's the transdichotomous RAM at the end. And the word RAM is a specific version of the transdichotomous RAM. Where you restrict the operations to C-like operations. These are sort of the standard. There are instructions on basically all computers, except, I mean, a few RISC architectures don't have multiplication and division, but everything else is on everything. So these are the operators, unless I missed one in C. They're all in Python and pick your most languages. You've got integer arithmetic, including mod. You've got bitwise AND, bitwise OR, bitwise XOR, bitwise negation, and shift left and shift right. Okay, these we all view as taking constant time. They take one or two integer inputs, words as inputs, They compute an answer, they write out another word. Of course, you can there's also random access, array dereference, I guess. Which you can, yeah. So that's the word RAM. You restrict to these operations. Whereas transdichotomous RAM, you can do weird things as long as they only involve a constant number of words. Word RAM, it's a regular thing. So this is basically the standard model that all integer data structures use, pretty much. If they don't use this model, they have to say so. Otherwise, this model has become accepted as the normal one. It took several years before people realized that's a good model, good enough to capture pretty much everything we want. Okay, the cool thing about word RAM is it lets you do things on W bits in parallel. You can take the AND of W bits pairwise all at once. So you get some speed up. But it's a natural generalization of something like the comparison model. Comparison model, I guess I didn't write those. Some more operations, less than, greater than, and so on. You can compare things, two numbers in constant time, get a Boolean output via, say, subtraction and computing the sign. And you think of comparisons taking constant time, so why not all of these things? Cool. One more model. Just kind of a weird one. It's called cell probe model, which is we just count the number of memory reads and writes that we need to do to solve a data structure query. Like you're looking at predecessor, and you just want to know how much of the data structure do I have to read in order to be able to answer the predecessor problem. How much do I have to write out to do an insertion, whatever. And so in this model, computation is free. And this is kind of like the external memory model and the cache oblivious models. There we're measuring how many block reads and writes there are. Here our blocks are actually our words. So there is a bit of a relation, except there's no real... You can either think of there as being no cache here, because you're just reading in a constant number of words, doing something, spitting stuff out. Or in the cell probe model, you could imagine there being an infinite cache for this operation, but no cache from operation to operation. It's just how much do I have to read in information theoretically to solve a particular predecessor problem. We'll deal with this a lot in a couple of lectures, not quite yet. This model is just used for lower bounds. It's not a realistic model, because you have to pay for computation in the real world. But if you can prove that you need to read at least a certain number of words, then of course you have to do at least that many operations. So it's nice for lower bounds. In general, we have this sort of hierarchy of models where this is the most powerful, strongest. And below cell probe, we have word RAM, or sorry, transdichotomous RAM. Then word RAM. Then just to fit it in context what we've been doing, below that is pointer machine. And below that would be binary search tree. Mentioned before, pointer machine is more powerful than binary search tree. And of course, we can implement a pointer machine on a word RAM. So we have these relations. There are, of course, other models, but this is a quick picture of models we've seen so far. Okay. So now we have this notion of a word. In the predecessor problem, these elements are words. They're W-bit integers. The universe is defined, and we want to be able to insert, delete, predecessor, and successor over words. So that's our challenge. For context, of course, I mean, in the binary search tree model, we know the answer to this problem is theta log n. In general, any comparison-based data structure, you need theta log n in the worst case. Easy lower bound. But we're going to do better on these other models, on the word RAM. So here are some results. First data structure is called Venom de Boas. You might guess it is by Venom de Boas, Peter. It actually has a couple other authors in some versions of the papers, which makes it a little bit confusing. But for whatever reason, the data structure is just named Venom de Boas. And it achieves log W per operation. I think I'll rewrite this. This is log U per operation. But it requires U space. So think of U space as being like, for every item in the universe I store, yes or no, is it in the set? So that's a lot of space, unless N and U are not too different. But we can do better. But the cool thing is the running time. This is really fast. Log U. If you think about, for example, I don't know, the universe being polynomial in N, or even if the universe is something like, polynomial in N is the same as like this, right, 2 to the C log N. You can go crazy and say log to the C power, so like 2 to the log to the 5th power. All those things, you take log twice, then log U becomes theta log N. So as long as your word size is not insane, you're getting log N. Is not insanely large, you're getting log N performance. So in general, when W is order log is polylog N, then we're getting this kind of performance. And I think in most computers, W is polylogarithmic. We said it has to be at least log. It's also generally not so much bigger than log. So log squared is probably fine for most of the time, unless you have a really small problem. Okay, so cool. But the space is giant. So how do we do better than that? Well, there's a couple answers. One is that you can achieve log W with high probability and order N space with a slight tweak. Basically, you combine Van and de Boas plus hashing, and you get that. I don't actually know what the reference is for this result. It's been an exercise in various courses and so on. I can talk more about that later. Then, alternatively, there's another data structure which in many ways is simpler. It really embraces hashing. It's called Y-fast trees, and achieves the same bounds. So log W, high probability, and linear space. It's basically just a hash table with some cleverness. So we'll get there. Even though it's simpler, we're going to start with this structure. And then it was, historically, this is the way it happened. Van and de Boas, then Y-fast trees, which are by Willard. And it'll be kind of a nice finale. So if we take there's another data structure I want to talk about, which is designed for the case when W is very large, closer, much bigger than polylog N. In that case, is something called fusion trees, and you can achieve log base W of N, I guess with high probability and linear space. The original fusion trees are static, and you could just do log base W of N deterministic queries. But there's a new later version that's dynamic, achieves this using hashing for updates, insertions and deletions. Cool. So this is almost upside down. It's obviously always an improvement over N, log base W of N. Always an improvement over just log base 2 of N. But it's sometimes better and sometimes worse than log W. In fact, kind of makes sense to take the min of them. When W is small, you want to use log W. When W is big, you want to use log base W of N. They're going to balance out when W is root 2 to the root log N, something like that. The easy thing is when these balance out is when they're equal, and that will be when this is log N divided by log W. So when log W equals log N divided by log W, let's do that over here. Log W is log N over log W. Then this is like saying log squared W equals log N, or log W is root log N. So I was right. W is 2 to the root log N, which is a weird quantity. But the easy thing to think about is this one. Log W is root log N. And in that case, the running time you get is root log N. So it's always at most this. And the worst case is when these things are balanced, and then the min of these two, or these two are the same, and they both achieve root log N. But if W is smaller or larger than this threshold, these structures will be even better than root log n. But in particular, it's a nice way to think about, oh, we're doing sort of a square factor better than binary search trees. And we can do this high probability in linear space. So that's cool. Turns out it's also pretty much optimal. And that's not at all obvious. And wasn't known for many years. So there's a cell probe lower bound. So these are all on the in the word RAM model. All these results. The first one actually kind of works in the pointer machine. I'll talk about that later. This lower bound's a little bit messy to state. The bound is slightly more complicated than what we've seen. But I'm going to restrict to a special situation, which is if you have n polylog n space. So this is a lower bound on static predecessor. All you need to do is solve predecessor and successor, or even just predecessor. There's no inserts and deletes. In that case, if you use lots of space, like U space, of course you can do constant time for everything. Right? You just store all the answers. But if you want space that's not much bigger than n, in particular if you wanted to be able to do updates in polylog, this is the most space you could ever hope to achieve. So assuming that, which is pretty reasonable, there's a bound of the min of two things. Log base W of n, which is fusion trees, and roughly log W, which is Van der Boas, but it's slightly smaller than that. Yeah, pretty weird. Let me tell you the consequences. A little easier to think about. Van der Boas is going to be optimal for the kind of the cases we care about, which is when W is polylog n. Sorry, yeah, polylog n. And fusion trees are optimal when W is big. Square root log n, log n. Okay, a little messy. So there's this divided by log of log W over log n. If W is polylog n, then this is just order log n, and so this cancels. This becomes constant. So in these situations, which are the ones I mentioned over here, W is polylog n, which is when we get log n performance, and that's kind of the case we care about. Van der Boas is the best thing to do. Turns out this is actually the right answer. You can do slightly better. It's almost an exercise. You can tweak Van der Boas and get this slight improvement, but most word sizes it really doesn't matter. You're not saving much. Cool. So other than that little factor, these are the right answers. You have to know about Van der Boas. You have to know about fusion trees. And so this lecture is about Van der Boas. Next lecture is about fusion trees. This result is from 2006 and 2007, so pretty recent. Okay. So let's start Van der Boas. Yeah, let's dive into it. I'll talk about history a little later. The central idea, I guess if you wanted to sum up Van der Boas in an equation, which is something we very rarely get to do in algorithms, is to think about this recurrence. T of u is t of square root of u plus order 1. What does this solve to? Log u. Right, just think of taking logs. This is the same as t of w equals t of w over 2 plus order 1. W is the word size. And so this is log w. Same thing. If we could achieve this recurrence, then boom, we get our bound of log w. So how do we do it? We split the universe into root u clusters, each of size root u. Okay, so if here's our universe, then I just split every square root of u items. So each of these is root u long. The number of them is square root of u. And then somehow I want to recurse on each of these clusters. And I only get to recurse in one of them. So a pretty simple idea. Now, yeah, so I'll talk about how to actually do that recursion in a moment. Before I get there, I want to define a sort of hierarchical coordinate system. This is a new way of phrasing it for me, so I hope you like it. If we have a word x, I want to write it as two coordinates, c and I. I'm going to use angle brackets so it doesn't get too confusing. C is which cluster you're in. So this is cluster 0, cluster 1, cluster 2, cluster 3. I is your index within the cluster. So this is 0, 1, 2, 3, 4, 5 up to root u minus 1 within this cluster, then 0, 1, 2, 3, 4, 5 up to root u minus 1 within this cluster. So those are the I is your index within the cluster, like this. And C is which cluster you are in. Okay, pretty simple. And there's easy arithmetic to do this. C is x integer divide root u, and I is x integer mod root u. I use Python notation here. So fine, I think you all know this. Pretty simple. And if I gave you C and I, you could reconstruct x by just saying, oh, well, that's C times root u plus I. So in constant time, you can decompose a number into its two coordinates. That's the point. In fact, it's much easier than this. You don't even have to do division if you think of everything in binary, which computers tend to do. So the binary perspective is that x is, it's a word, so it's a bunch of bits. Right? 0, 1, 1, 0, 1, 0, 0, 1, whatever. Divide that bit sequence in half, and then this part is C, this part is I. And if you assume that W is a power of 2, these two are identical. If they're not a power of 2, I mean, you've got to round a little bit here. It doesn't matter, but you can use this definition instead of this one, either way. So in this case, C is, oh boy, x shifted right, W over 2, basically. So this is W over 2, W over 2. Whole thing is W bits. So if I shift right, I get rid of the low order bits. If I want I, it's slightly more annoying, but I can do it as an AND with 1 shifted left, W over 2, minus 1. That's probably how you do it in C. I don't know if you're used to this, but if I take a 1 bit, I shift it over to here, and I subtract 1, then I get a whole bunch of 1 bits. And then you mask with that bit pattern. So I'm masking with 1, 1, 1, 1. Then I'll just get the low order bits. And computers do these super fast, way faster than integer division. Because, I mean, this is just like routing bits around. So this is easy to do on a typical CPU, and this will be much faster than this code, even though it looks like more operations typically. All right, so fine. Point is I can decompose x into C and I. Of course, I can also do the reverse. This would be C shifted left, W over 2, ORed with I. Okay, so slight diversion. Now I can tell you the actual recursion and then talk about how to maintain it. So we're going to define a recursive Venom-de-Boa structure of size U and word size W. And what it's going to look like is we have a bunch of clusters each of size square root of U. Okay, so this represents the first root U items, this represents the next root U items, this represents the last root U items, so on. So that's the obvious recursion from this. So this is going to be a Venom-de-Boa structure of size root U. And then we also have a structure up top, which is called the summary structure. And the idea is it represents, for each of these clusters, is the cluster empty or not? Does this cluster have any items in it? Yes or no? If yes, then the name of this cluster is in the summary structure. So notice by this hierarchical decomposition, the cluster number and the index are valid names of items within these substructures. Basically, we're going to use the I part to talk about things within the clusters, and we're going to use the C part to talk about things within the summary structure. They're both numbers between 0 and root U minus 1, and so we get this perspective. All right, so formally, or some notation, cluster I, so we're going to have an array of clusters, is Venom-de-Boa's thing of size square root U, and word size W over 2. This is slightly weird because the machine, of course, its word size remains W. It doesn't get smaller as you recurse. We're not going to try to spread the parallelism around or whatever. But this is just a notational convenience. I want to say the word size conceptually goes down to W over 2 so that this definition still makes sense. Because as I look at a smaller part of the word, in order to divide it in half, I have to shift right by a smaller amount. So that's the W that I'm passing into the structure. Okay, and then v.summary is the same thing. It's also a Venom-de-Boa's thing of size root U. Then the one other clever idea, which makes all of this work, is that we store the minimum element in v.min. And we do not store it recursively. So there's also one item here, size 1, which is the min. It's just stored off to the side. It doesn't live in these structures. Every other item lives down here. And furthermore, if one of these is not empty, there's also a corresponding item up here. This turns out to be crucial to make Venom-de-Boa's work. And then v.max we also need, but it can be stored recursively. So just think of it as a copy of whatever the maximum element is. Okay, so in constant time, we can compute the min and compute the max. That's good. But then I claim also in log W time, log U time, we can do insert, delete, predecessor, successor. So let's do that. This data structure, the solution is both simple and a little bit subtle. And so this will be one of the few times I'm going to write explicit pseudocode, say exactly how to maintain this data structure. It's short code, which is good. Each algorithm is only a few lines. But every line matters, so I want to write them down so I can talk about them. And with this new hierarchical notation, I think it's even easier to write these down. See how I do. Okay, so we'll start with the successor code. Predecessor is, of course, symmetric. And it basically has two cases. But there's a special case in the beginning, which is if the thing you're querying happens to be less than the minimum of the whole thing, then of course the minimum is the successor. This has to be done specially because the min is not stored recursively. And so you've got to check for the min every single level of the recursion. Okay, but that's just constant time, no big deal. Then the interesting thing is that we have recursions in both sides, in both cases, but only one. The key is we want this recurrence, t of u is 1 times t of root u plus order 1. That gives us log u. If there was a 2 here, we would get log u, which is no good. We want the 1. So in one case, we call successor on a cluster. In the other case, we call successor on the summary structure. But we don't want to do both. Okay, so let's just think about intuitively what's going on. We've got this, I guess I can do it in the same picture. We've got this summary and a bunch of clusters. And let's say you want to compute what's the successor of this item. So via this transformation, we compute which cluster it lives in and where it is within the cluster. That's I. So that's some item here. Now it could be the successor is inside the same cluster. Maybe there's an item right there. Okay, then I want to recurse in here. Or it could be it's in some future cluster. So in that case, okay, well let's do the first case. If basically we are less than the max of our own cluster, that means the answer is in there. Right? Figure out what the max is in this structure, the rightmost item in S that's inside this cluster C. This is C. If our index is less than the max's index, then if we recurse in here, we will find an answer. If we're bigger than the max, then we won't find an answer down here. We have to recurse somewhere else. So that's what we do. If we're less than the max, then we just recursively find the successor of our index within cluster C. And then the answer, we have to add on the C in front, because successor within this cluster will only give a name or give an index within the cluster. And we have to prepend the C part to give a global name. Okay, so that's case one. Very easy. The other case is where we're slightly clever, in some sense. We say, okay, well, if there's no successor within the cluster, maybe it's in the next cluster. Of course, that one might be empty, in which case it's in the next cluster. But that one might be empty, so look at the next cluster. We need to find what is the next non-empty cluster. For that, we use the summary structure. So we go up to position C here. We say, okay, what is the next non-empty structure after C? Because we know it's whatever. That's going to be where our answer lives for successor. So that's going to give us basically a pointer to one of these structures, C prime, which all these guys are empty, and so there's no successor in there. The successor is then the min in the structure. So that's all we do. Compute the successor of C in the summary structure, and then in that cluster, C prime, find the min, which takes constant time, and then do C prime, prepend C prime to that to get a global name, and that's our successor. Yeah, question?
Could you repeat why min is not recursive? Because looking at this, it looks like all of these smaller 3D trees have mins associated with them.
Okay, sorry. Question is, why is the minimum not recursive? The answer to that question is not yet clear. It'll have to do with insertion. But I think what exactly this means, I maybe didn't state carefully enough. Every Van Underboe structure has a min, stores a min. Okay, in that sense, this is done, it sounds funny, not stored recursively, but everyone stores it. The point is that this item doesn't get put into one of these clusters recursively. Just the item. But each of these has its own min, which is then not stored at the next level down. And each of those has its own min, which is not stored at the next level down. Think of this as kind of like a little buffer. The first time I insert into the structure, I just stick it in the min. I don't touch anything else. Afterward, well, you'll see when we get to the insertion algorithm. But it sort of slows things down from trickling.
So is that so putting that min, is that what prevents from sort of
That will prevent the insertion from doing 2 recursions instead of 1. So we'll see that in a moment. This point, just successor is very clear. This would work whether the min is stored recursively or not. But we need to know what the min is of every structure. We need to know the max of every structure. At that point, I mean, at this point, you could just say that min and max could be copies, no big deal, and we'd be happy. And of course, predecessor does the same thing. Okay, so the slight cleverness here is that we use the min here. This could have been a successor operation with minus infinity as the query, but that would be 2 recursions. We can only afford 1. Fortunately, it's the min item that we need. So we're done with successor. That was the easy case, or the easy one. Insert is slightly harder. Delete is just slightly messier. It's basically the same as insert.